out the way you can, but you have to apply it very soon. Very soon. Let's see. Think about it. Okay, so we were talking about what? Less than or equal to. There is one very now. I mean, you can. I have written the proof. You can go through it. No, they are not difficult, but it's good to know key points. That's why I am doing it. Yeah. There is a remark here in my note. It's again in the book, by the way. There is one very important difference between subset relation. The subset relation is making. Subset relation and less than proper subset relation, and there is a difference. Given any two distinct natural numbers n and m, if you are given two distinct natural numbers, we know either n less than m or m less than n. One of them is true. But if you are given two sets, A and B, A is not equal to B, you cannot say A is subset of B or B is subset of C. You cannot say so. That is a way. Though less than or equal, these are very similar, this is a very big difference, because you can take two sets, for instance, 1, 2 and say 3. You cannot say this is subset of this, or this one is subset of this. You cannot say so. But for numbers, if they are distinct, one of them is smaller than the other. This is a very important thing. For instance, there is an example here. This is why we say that sets are partially ordered. Partially ordered. The natural numbers are totally ordered. You are going to learn these two words to some depth later. The sets are partially ordered. They are ordered but not completely. Partially ordered. Numbers, not only integers, real numbers are totally ordered. Remark, I have here 2 belongs to the set 1, 2, 3, but 2 is not the subset of 1, 2, 3. In fact, 2 is not the set. Conversely, singleton 2 is subset of set consisting 1, 2, 3, but I guess they are clear. You can either read my notes or the book. N is infinite and its elements are finite. This is an important fact to remember. This set N is infinite. Again, if it is mathematical, we have to know the meaning of infinite. So far, we don't know it. It is taken for granted that we know N is infinite. However, all the elements are finite. 1, 2, 3, 4,000 million, whatever. Now, if you take this set has Z, N, Q, R. This set is finite, but its elements are infinite. Finite is infinite. Axiom of specification. This is not very exciting to me, but I don't know whether there is a reason not known to me. As a result, I got it. Sometimes, if you have very good scores in TOEFL as well as what is called GRE. If you apply very good universities, sometimes they give full scholarship that way also. But you don't get that much money, like 95,000, but you get full scholarship. Mean what I meant was airfare and tuition is of course covered, and some money. Again, for you don't have time to any of this. Now I guess you have to do the degree here, I think. So I will think about, see whether there is an escape route. What is this axiom of specification? This is new to me, and I don't knew, the name is new to me, but the result is of course very natural. Let capital A be a set, and for each x belongs to A, let Px be a property pertaining to x. That is, Px is either a true statement or a false statement. Px is a statement about x. It could be x squared greater than 0, something like that. Then there exists a set called set of all x belongs to A such that Px is true, whose elements are precisely the elements x in A for which Px is true. In other words, for any object y belongs to set of all x belongs to A such that Px is true, if and only if y belongs to A and Py is true. This axiom is also known as the axiom of separation. It is clear that set of all x belongs to A such that Px is subset of A. I don't know where this will be important. However, the thing is that it exists. Now, he said that empty set exists. He proved that given any object A, this one exists. Like that, if you are given capital set A, and if you are given a property Px, then what he says is set of all x belongs to A such that Px, there exists a set like this. So in general this is taken for granted in general, but somebody can ask, no, how do you know that there is an empty set? How do you know that there is a singleton? How do you know that there is such a set? So answer is axiom. It is like your father is a doctor, no? Because I was also medical doctor, no? So I was also president of some doctors association for 3 or 6 years. Then I learned something. You are a surgeon, you do something. Oh, no, you don't have to be a surgeon. You do give some medication to some patients. Went wrong, he died. What is the excuse? දොස්තරලා කියන්නේ මොකද්ද in Sinhala? He's allergic to the medicine. That's the way, where is it? You know, it's like in Sinhala, okay, so what he is saying is, to us, this is in nothing really exciting, but to the contrary, if you are given a capital set A, set capital A, sorry, my English is incorrect, and a property Px, set of x belongs to A such that Px is true, such a set exists. That's what it says. So he is labeling it as axiom of specification. Definition, intersections. Now we are getting to a little bit of maths, little bit. The intersection S1 you have two sets, S1, S2. The intersection S1 intersection into S1 intersection S2 of two sets is defined to be the set. This is the set. So he says set of all x belongs to S1 such that x belongs to S2. I mean, this is how he defines. And this is the same thing for us. Set of all x belongs to S2 such that x belongs to S1. Oh, this is set of all x such that x belongs to S1 intersection. Oh, S1 and S2, sorry. Same thing, but this is his definition, no? He has this. Is there an English word for this thing? I don't know. Somehow I learned something. Did you know? I mean, I don't know about you. This person extremely good at punctuation, no? Exceptionally good. I have been trouble in punctuation. He is, I guess, the best in the world in punctuation. Anyway, so I guess you knew the intersection when you were doing O level. For he says thus for any object x, for any object x, x belongs to S1 intersection S2, if and only if x belongs to S1 and x belongs to S2. Then he says two sets AB are said to be disjoint. This is an important word, you need to know that. Disjoint means disjoint if A intersection B is empty. This is the meaning of two sets are said to be disjoint, A intersection B is empty. Two sets AB are distinct if A is not equal to B. So two different. Disjoint means A intersection B is empty. Distinct means they are not the same. For instance, 1, 2, 3. Here you have 1, 2, 4. Distinct sets. These are distinct. 1, 2, 3. 1, 2, 4. Distinct. Why? Because they are not the same. Number 3 is here, it's not over there. Number 4 is there, and number 3 is 4 is not here. And 1, 2, 3, you know all these little things. 1, 2, 3 intersection. 1, 2, 4 is obviously this is set. Pair set consisting 1 and 2. Meanwhile, empty set and empty set are. This is empty set and empty set, they are disjoint. Why? Because this one intersection, this one is empty. But not distinct. They are not, we proved that there is one and only one non-empty set. So empty set and empty set are disjoint but not distinct, so he is pointing out that. Different sets. Just
that should be B. Distinct if A not equal B.
yeah, distinct. It's important that you point it out. Then he is talking about difference of two sets. Most of these things, union, intersection, all of them we talk about for two sets, like all are binary, only two. If A and B are sets, A, B are set, we talk about the difference. Difference, D-I-double-F-A-R-E-N-C. Differences. A, we write either this way or A minus B or A minus B. This is the famous one. You don't, I don't write this way at all, and in many books this is A minus B. This is actually, to think this way, you subtract from A
the elements of B.
Elements of B. That's what it means. So we have written the definition: X belongs to A such that X is not in B. This is it. he says A minus B to be the set A with any element of B removed. Yeah, it's a good way to say it. For instance, here 6, 8, 9, 10 minus 6, 8, 10 is equal to what? Only 10. 9. Like this. So now you know the meaning of A union B, A intersection B, and A minus B. There is an important thing that you know A union B is equal to B union A intersection B is equal to B intersection A, but A minus B may not be equal to B minus C. There are times at which they are the same. It's like, even for numbers this is true, no? 2 minus 3 is not equal to 3 minus 2, like that. This is, however, this is empty set minus empty set is empty set. I mean, these are very exceptional situations. But in maths, exceptional points are very important. Then proposition sets form a Boolean algebra. There are, I guess, I don't know, bunch of properties. Let me write because they are important for you to know. They are very simple. He has given names for them. Boolean algebra. I guess you have to learn Boolean algebra. You know, no? We don't need to know much Boolean algebra. ABC are sets. A, B, C are sets. Assume that is inside X. So what it is minimal element. He talks about minimal element. Minimal element. We have A union, empty set is empty set. A union, empty set is A, and A intersection empty set is empty set. So empty set is like the smallest element, no? Whether you add empty set, it does not change. That kind of idea here. The maximal element, I don't know why he gave these names, whether it is that important. A union X is equal to X. A intersection X is a identity. A union A is A as well as, oh, sorry, I did not write. A intersection A is also A. It's very easy to prove all of them. A union B, commutativity. A intersection B, first A union B is equal to B union A. Though these are very easy, prove them because then it gets to the habit of writing proofs. That's very important. A union B is equal to B union A. Associativity. We have discussed all of them. Associativity. A intersection B intersection C is A intersection B intersection C. Some of them we have already proved, by the way. Distributivity. We haven't proved, I guess, BUT. A intersection B union C. We distribute A intersection to both B and C. A intersection B, union A intersection. So that's why we call it distributive. A intersection is distributed to both B and C. And A union B intersection C, then we distribute A union, then you get A union B intersection A union C. So distributivity. Partition. Prove it. Though they are certain things are very easy to prove. So, but very important that prove it. It is good for you. Because you need to get to the habit of writing. This is partition. Partition. A union x minus A is x. A intersection x minus A is empty. De Morgan's laws, these are very important by the way. De Morgan. De Morgan's law. I don't know. I usually write De Morgan's law. Morgan is a person. So in this book it is De Morgan. I guess this is the first time I noticed some English problem. Because this book is expert in English. These are very important by the way for you. X minus A union B. First one is A union B, yeah. Is equal to X minus A intersection X minus B. In logic, now let me write the other one also first. X minus A union, A intersection B is X minus A union X minus B. It is like not, this one is not. I don't know whether I gave you as an homework, not. Here X is a set, here X is a statement, not X or Y. Is, I guess we discussed this, no? Not X and not Y. Negation of X or Y, we discussed, no? Same thing here. Not, this is A union, X belongs to A, or X belongs to A, no? Same thing. Next one is E not equal if and only. Next one is not X and Y, if and only if, not X, O, not Y. Union is like O, intersection is like N. So De Morgan's laws. This is also De Morgan's laws. This is also De Morgan's laws. So there is anything called generalized De Morgan's laws. I will do it someday before the course is over, when that kind of thing is important. And proof. Book says exercise. I also said the same thing. And I don't think anything here is difficult. This one. Actually, no. It's a simple. Do you observe some symmetry in the above laws between union and intersection? You can see right away some symmetry. And between X and empty set. This is an example of duality. I myself don't know the real meaning of duality. because I studied Banach spaces, then dual of Banach space is very important. Here it's a different meaning. It's like a taste of curd. I eat curd, you eat curd, I know the taste of curd, you know the taste of curd. I don't know whether you will taste the way I taste, you know what I mean? Something like dual, meaning of dual, I cannot say. I guess, everybody says, I know. Same here. This is an example of duality, two distinct properties of objects being dual to each other. Maybe I should take a look at the dictionary because since I studied analysis, dual is a very, very important word. You have heard the word Banach spaces? No, not yet. Then best not say. In this case, the duality is manifested by the complementation relation A to x minus A, the De Morgan law has. It's not clear. He also did not say. He is also talking about how one feels. It is also interchange section where he said, can you see here empty set X sort of? If you take the empty set A union empty set A union X, kind of. Let me take a look at the meaning of dual in an English dictionary and tell you whether I will understand the meaning. So, but what you see is what it means. Precisely, I cannot say. The above laws are collectively known as the laws of Boolean algebra. Boolean algebra. So let's just say what he says, because so far we don't know what Boolean algebra is. I don't want to spend any time about the Boolean algebra because I am in a rush to go to analysis, not to Boolean algebra. Axiom, there is axiom here, replacement. Let capital A be a set. Again, the same kind of thing is making an axiom, so we have to write because it is an axiom. What he says is that let capital A be a set for any object x in A and any object y. Suppose you have a statement Pxy pertaining to x and y, such that for each x belongs to A, there is at most one y, for which Pxy is true. Then there exists a set of all y, such that Pxy is true, for some x belongs to A. Actually, this one, you have taken it for granted. But what he is saying, there is such a set. It is an axiom. You have a set capital A. Then you have for each x belongs to A. For each x belongs to A. And any object y. Oh, any object y. So any object y, suppose you have a statement Pxy. Pxy may be like x squared plus y squared is equal to, say, greater than or equal to 4. That kind of some statement, depending about Pxy is a statement about x and y in simple English. So he is saying pertaining to x and y, such that for each x belongs to A, there is at most one y. For each x in A, there is at most one y. There is at most one y, such that Pxy is true. Then what is there? Then then he says, then there is a set. What is the set? Set of all y such that Pxy is true for some x belongs to A. I mean, the thing is that you can talk about this set. What the axiom says is there is such a set by axiom. Without this axiom, you may say consider the set of all y such that Pxy is true for some x belongs to A. I mean, here he is saying, if somebody asks you, how do you know that there is such a set? You can say by replacement axiom. That's all. He is saying there is such a set. That's all he says. Example, he says, let's take A is equal to 359 and let Pxy be the statement y equals x plus plus, that increment. Then y is the successor of x. Observe that for each x belongs to A, there is exactly one y for which Pxy is true. To define this set, you have to have at most one y, in this case exactly one y. Successor is unique, no? Exactly one y for which Pxy is true, especially the successor of x. Thus the above axiom asserts that the set of all y such that y equals x plus plus for some x belongs to 359 exists. In this case, for every x in 359, you have the successor, so you get 416. I mean, it is what certain says that existence we take for granted. He says they exist by some name given by axiom, some axiom. That's what he does. So actually, in my case, I haven't seen this kind of axioms before, because I take this for granted. I mean, it is true. What do we mean axioms? But it's a theory. Nothing can be, in maths rather, nothing can be taken for granted without a proof or without an axiom or anything. Otherwise, maths won't survive. Even now, today's world, incompleteness, you know the incompleteness of mathematics. People ask, mathematicians are scared whether somebody who does not know anything will come and say something which collapses mathematics. So when I was at Ohio State, I was a professor there. We have twice some colloquia in the maths department. I go there, especially because of math. They give so much of food to eat. At every meeting they talk about that whether somebody will come and say something. Layman, somebody who does not know math, will come and say something that we cannot believe. It is possible. That is why this kind of axioms are very important, to make sure that there are no gaps, that there is nothing that we overlook or else we didn't pay attention. That is why these axioms are important. But to us, I mean, we don't need any axiom, no. There is such a set. Why on earth we need? If this some relation between x and y, we say consider the set. We take it for granted, but in maths, no. They have to make sure that there is such a set. So it is taken. They have come up with the axiom and labeled it as axiom of separation. We abbreviate a set of this form, set of all y such that y is equal to fx for some x belongs to A, or fx x belongs to A, you can see. By the way, this I always write set of all fx such that x belongs to A this way, but some people write this set of all fx such that this way, x belongs to A. This is another way of writing such that in a set only. Axiom infinity. I don't know why it's this infinity, but it's axiom also we have to go through it since we are studying this book. Maybe he's using, if he says this is by axiom infinity, We need to know what it is. There exists a set n, set of all natural numbers, whose elements are called natural numbers, as well as an object 0 in n, and an object n plus plus assigned to every natural number n in n, such that piano axioms 1 to axiom 5 hold. That is axiom infinity. So he has many axioms. You cannot remember it. Don't try to remember these axioms, but remember that you have seen them. That's enough, because you cannot remember. You are not here to cram and remember axioms. You are passing these axioms to make sure that before you start doing analysis, you have seen these very basic words. This is the more formal version of assumption made earlier. It is called the axiom of infinity because it introduces the most basic example of an infinite set. That is true because this is the most basic example of an infinite set. Somebody asks you an infinite set. If somebody asks you a real number, usually you will say 1. If somebody asks you an infinite set, you also say n. N comes right away. The following two sets are equals. Another thing is, same set can be written in different ways. N plus 3 such that n belongs to n. This set is equal to this set, 8 minus n, such that n belongs to n. Oh, I'm wrong. Oh, I am wrong. Set of all n plus 3. Such that n belongs to n, and n lies between 0 and 5, including both of them. This set is equal to set of all n minus 8 minus n, such that again n belongs to n, and n lies between 0 and 5, including both 0 and 5. So what this example is, when you look at this at first, you don't think they can be equal, because one thing is, it is confusing, by the way. Here you have when you have the same letter A, then it's a variable no here. When you have the same variable in either set, it's confusing. You cannot understand. Actually, there is no n for which n plus 3 is equal to 8 minus n. If so, 2n is equal to 5, then n is equal to 5 by 2. So, though these two sets are equal, for no n, this one is going to be equal to that one. So, this is, and having the same variable n in both sets, it makes life difficult. You get confused. We try to avoid that quite often. Not quite often, almost all the time. If you write this set, if n is equal to 0, this is 3. If n is equal to 1, this is 4. If n is equal to 2, this is 5. If n is equal to 3, this is 6. If n is equal to 5, this is 8. No? So this is this set. And this set is 8 minus 0 is 8. 8 minus 1 is, did I do something wrong? 8 minus 10.
8 minus 1 is 7.
8 minus 5 is,
No.
8 minus 0 is 8, no? 8 minus 1 is
7.
And I have done something wrong here, no? When
No,
n
you
is
missed
equal to
the 7.
5, 6, 7. 0 is 3, 3, 4, 5. Then what?
6.
6. 6. 0, 3,
2, 3 plus 3 is 6.
6. Then 8, right?
7. 6, 7, 8. 4 plus 3.
0 plus 3 is 3.
Yeah.
1 plus 3 is 4. 2 plus 3 is
5.
5. 3 plus 3 is
6.
4 plus 3 is
7.
7. That's 5 plus 3 is 8, right?
Yeah.
Now this. Here again, if you plug 0, you get 8. When you plug 1, 7. When you plug 2, 6. Then, anyway, you will see 5 over 3, 2. 3, no? By looking at the two sets, I mean, in English they say looks are deceptive. No? They say by cover of the book you cannot tell about the book, because one student who is doing physics special one day, he has been to Colombo University library, science library. He has seen this book and they know about me, Colombo University students, they know about me very well. Oh, there are baby books in the library. This book has terribly advanced mathematics. Yeah, buy the book, you can say. That's how some people talk. So, what I am saying is, though these two sets are equal, you cannot see at once, looks are deceptive. And the funny thing is, n plus, one may try to, if you are asked to prove this thing, sometimes one may try to solve n plus 3 x is equal to 8 minus n. There is no single n for which they are equal. So, what do I say here? Even though the expressions n plus 3 and 8 minus 1 are never equal to each other, when you have the same letter, when you are doing, it is always good to have a different letter. 8 minus m, m belongs to n, and 0 less than or equal to m less than or equal to 5. Much less confusion by writing this. Writing this. Same set, no, whether you write in no m or whatever. Like this. Okay, then we are coming to a good word, functions, because analysis is about functions. So now we have come to that word. Again, he is writing the definition in somewhat different way. You have the notes up to functions, no?
Yeah.
Okay. In order to do analysis, we need the notion of a function.
Up to page 12.
Up to page 12. Analysis 12. Yeah, that's something. I went through, I guess, a whole bunch of them. Yeah, there are some more ways. In order to do analysis, we need the notion of a function from one set to another. Actually, analysis is about functions. And I did analysis. So I analyzed functions. So now here in undergraduate courses, you don't analyze functions, you study about functions, one function. Anyway, informally a function is now, since we are going to functions, let's erase all of them. Functions. Your other classes are going on, no? Statistics and Dr. Rabat class. Am I going very slow for you? Because the thing is that I need to, tell I cannot see because this is not a novel. That is why I have to go through everything. Formally a function, this is how we write f, x, arrow, y. This is an arrow. So this is from one set x to another set y is operation which assigns to each element is an operation, a and n is missing here, assigns to each element. If you take any element here, we call them input. It is like a machine. F is a machine. You put x, simple x to the machine, you get output fx. X input. It is like a machine. This is the machine. F. You take x. This is y. Machine gives you fx. So that's what it does. F is actually, it is like an operation, like a machine. When you put simple x to the machine f, input x, you get output fx. To each element, O input simple x in x, a single element, O output fx in y. The formal definition is as follows. It is definition. I suppose this one is making kind of little difficult the definition of a function. Let x, y be sets and let p, x, y be the somehow actually this is enough for you to do mathematics. F is for any simple x in capital X, you get exactly 1y output, one output fx. That is a function. For any x, if you take any x, there is one fx belongs to y. That is a function. He's making axioms. No, let xy be sets and let pxy be a property pertaining to object simple x in x and object y in y, such that for every x in x there is exactly one y belongs to y for which way pxy is true. So it is making a little difficult. You have the pxy. What he says is, if you take any simple x from capital X, there is exactly one y in capital Y, so that pxy is true. There is exactly one y belongs to y, which pxy is true. This is sometimes known as vertical line test. You know that, no? To check in A level. So if somebody gives you, is this a graph of a function? You say no, because when you draw a vertical line, it cuts at two places. This is not a graph of a function. Why? Because vertical line, two places. So horizontal line, there is in A level you have vertical line test to check whether it is a function. Horizontal line test to check whether it is one to two tests. So this is vertical line test. This is sometimes known as the vertical line test. Then we define the function fx to y defined by p on the domain x and range y to be the object which, given any input simple x in x, assign an output fx belongs to y, defined to be the unique object fx belongs to fx, for which px fx is true. Thus, for any x in x and y in y is equal to f, y belongs to y equals fx. He says, if and only if pxy is true. So what he says is that you have this pxy here is a statement about simple x in capital X and simple y in capital Y. What it says that for any simple x in capital X, there is exactly one y such that pxy is true. Actually, that is indirectly he is talking about that what we know about the function. So that y then he defines as fx. That's all he does. So it is again nothing new, but you need to have seen this thing. That's why I am going through them, though they are not going to help you too much. Example then, let x equals n, y is equal n, and let pxy be the property that y equals x plus plus. You have here n, here is also n, then your y is, your pxy is, your pxy is x plus plus. This is a relation between x and y. Pxy is this. So according to this one, this for any x in n, there is exactly one y in n, such that pxy is true. In this case, y is x plus plus. So y, you can say fx equals x plus plus. So nothing is new in this paragraph. However, thus we can define the function f2n associated to this property, so called fx equals x plus plus for all x. This is the increment function n. Thus, for instance, f4 is 5, we know all of them. Then one might also hope to define decrement function. Decrement function you cannot define this way, because if you take 0 here, 0 cannot be something plus plus, no? So then you have to change, I guess, this side, you have to delete 0, then you can define, just read it, it's no big deal. However, in this case it is y plus plus is equal to x. In this case, other way, cy, no big deal. But the most important thing you to know is, if you have, say, real numbers to real numbers, fx equals x squared is a function. We will be talking about this kind of functions very soon, without going through this pxy story. He is making sure that they exist and there are no holes in pure mathematical. One might also, no, that's it, forgot it. So I won't go through that line. One common way to define, that's a good one for us. One common way to define the function, this is on page 14, define the function is simply to specify its domain, its range, and how one generates the output fx from each input text. Again, you don't need that much. I'll tell you why. I will tell you why. So function is a very important word, by the way. Very soon we are going to deal with functions. Properties of functions. We are getting there. So far we are talking about basics. One common way to define the function is simply to specify its domain. Say for instance x. And its range. Let's take range. How one generates output fx from each input x. You have, say, f, you put x, you get fx. Can you see here, though he says you need the domain, you put to the f elements of x. Then fx, we don't really need capital Y, because can you see, if you are defining a function fx equals x squared. Then x belongs to R, not real numbers. We really don't have to say why, because say for instance f going from R, I'm sort of jumping, sorry about jumping, say fx equals e to the x, assuming this you know that I'm jumping to explain meaning e to the x, e to the fx equals e to the x over e to the x plus 1. So actually this is going to 0, 1 open interval. Though I am saying going to R, that is true, but it's small set. Same thing can be, function can be written R to 0, 1. F of x is equal to e to the x over e to the x plus 1. Can you see? This, I mean, capital X is very important, but when we say capital Y, it's not exactly the range, you know. For this function, range is open interval 0, 1. E to the x, if you take any x, e to the x over e to the x plus 1, this one strictly less than 1, strictly greater than 0, for any x, for x belongs to R. I think it is correct. I haven't done analysis for a long time, but I think it's true. So what I am saying is here, capital X is very important. Capital Y, we may not be going to the whole capital Y. It could be like we are going to small set. And not only that, you can say f going from R to R, you say fx is 1. Actually, I went to R, so far he has to talk about real numbers. I just jumped, but I just want to explain that we need the whole set capital S, but we may not need capital Y here if you want. I mean, like this way, you can construct so many examples. Range is not all of us. Here, so I like this definition. One common way to define a function is simply to specify its domain. That is very important. And how one generates the output fx from each input x. Here there are two examples. N to n. One is fx equals x plus plus, successor. Next one is f going from 0 infinity to left close 0 infinity interval to left close 0 infinity fx equals root x. This is a function. If you take any non-negative real number, it has a square root which is also non-negative. No? If f is a function, f x to y, then set of all, this is called the graph of f. Set of all x f x such that x belongs to x, I guess, so where am I? Yes. This is called the graph of f. Actually, now for instance, suppose you take that fx equals x squared. Then you get this graph, no? This is the graph. This set is this one. Fx equals x squared. It's the English word is. We call the graph to this picture. In mathematics, this set is called the graph. Then picture of this set is this one. If you go to any point, y coordinate is x squared, x of x. So else, when fx is x squared, This is x square. No? So we think that when we say that is the graph, to us it is the, but in math is that set of all except x. That is the graph. Definition. So these are good words because we are getting to some mathematics, specification, axiom, all these. Enough ideas, no? But we need now we have seen them. That's important. You should have seen them, and we have seen many of them. Equality of functions. Two functions f x to y, g x to y with the same domain and range are said to be equal. Right? F equals c if and only if fx equals gx for all x belongs to x. That's important. Two functions, if you want to say two functions f and g are equal, f and g are equal, how do we, they have to have the same domain, no? Let me write out of the note to you for analysis. If you want to say these two are equal, domain of f must be equal to domain of g. So, they must be the same domain G. Same set. And if it's, let's say this is for instance capital X. So in order for the function f to be equal to the function g, this must be the case, and set of all x belongs to x, x belongs to capital X, fx must be equal to gx. This is how usually how we say the two functions f and g are equal. They have to have the same domain, and in domain each element has to have the same image under both f and g. That's how we equate two functions. Actually, he also has written almost the same thing. The reason I did not write why is sort of redundant. As I told you from my examples, for this function, for instance, say fx equals x squared. Somebody can say this is going from r to r. Somebody else can say this is going from r to 0 infinity. Not the same way, because if you take a real number, square is always greater than or equal to 0. But capital X, the domain is very important. Same domain for two functions to be equal. They have to have the same domain, though it says they have to have the same range. I don't emphasize it because sooner or later we are going to study analysis within 1 or 2 weeks or 3 weeks. Then this is what is important for us. What is in the book is not wrong, but this is enough for two functions f and g to be equal. They have the same domain. For anything in the domain, both outputs are the same. Examples I have written here. You can go through it. Now what? Here I'm talking about one example. Let me spend a couple of minutes with it. I am considering this one, f going from 0 infinity to 0 infinity. This function f is given by fx equals x. And the other function g going from 0 infinity to 0 infinity. This gx is mod x. They are different looking. They have the same domain. I just wrote the range also, it's going from 0 to infinity. But the formula, output, here I am saying output is fx equals x. Here for this function output is equal to mod x. Appear different. No?
So there are two f's.
Am I tired? No. Now, I told you when I was in USA, I don't walk, I always write. That's why I became the most popular professor. Last day of lectures, because I talk about, in Sri Lanka, I talk about Kavum, Gogis, Dodal, etc. Over there, I talk about pizza and coke. Last day, they bring so, at least I get like 15 pizzas. They bring, put on my table with several bottles of coke. I cannot take them home even. I always talk about pizza. Actually, used to like pizza a lot. Now, I cannot eat that much pizza. It's too bad. You also should eat when you are very young. You get old, you cannot eat. Too bad. Now I cannot run. The Ohio State had 350 professors of mathematics, very big university. So I was over there very popular as the most popular professor, very popular. Because I was so active, and I like students by the way. Oh. And I'm very energetic. With the age, you lose your energeticness. You run away. After another 5-10 years, maybe I cannot lecture. I don't know. It can happen. How some people teach in USA. Professor Rose, have you heard? It's a number theory person. Yeah, anyway, he has international workshops during the summer. He was 90. Still he was conducting. Because he is so crazy about numbers. That is why. He didn't want to spend one summer without playing with the numbers. But he passed away when I came home. After I came home, he passed away. Now, here, when you look at here, both domain of f, let me write in English because no notation. Domain of f is equal to domain of g is equal to left close 0 infinity interval. I say left close because of this parenthesis. If I had this way, I will say left open because it is open. And also for each x belongs to infinity, 0 infinity, left close 0 infinity. Fx, gx is mod x. Since x is non-negative, mod x is x, no? This is equal to fx. So can you see here, they are different looking, but I have shown, of course they have the same domain, but then I have shown for any element in the common domain, gx and fx are equal for each x. Thus, f is equal to g. So that what I am saying here is that for two functions to be equal, you don't have to have the same expression. Like that two sets, One was n plus 3, other one was 8 minus n. Different looking, but to the contrary, they are the same. Here, looks are different or deceptive, you know what I mean. Now let F R to R also, let me read it. If you like math and if you like students, teaching is a real good job. Oh, I enjoy so much in USA and here in Sri Lanka also. But you have to know the subject well. If you are scared of the students, they will ask you questions I cannot reply. You cannot enjoy. And if you are not willing to say I don't know, again you cannot enjoy. Because for instance, you three can ask me a question that I cannot reply. If I am going to answer the questions that I don't know how to answer, I am in trouble. So you have to study hard and be better. Teaching is not that much money, but you will forget money. You enjoy teaching a lot. Okay, now let F R to R by Fx equals x and G R to R by Gx equals mod x. Then domain of F is equal to domain of G. By the way, you want to be a professor of maths? Oh, that's very good. It's kind of fun. Domain of F equals domain of G is equal to R. F of minus 1 is, in this case, F of minus 1 is minus 1. G of minus 1 is, absolute value of minus 1 is 1. So, F of minus 1 is not equal to G of minus 1. Thus, F is not equal to G. Here, F is equal to G over there. Again, what I am saying is here, just because of it is the same, in this case, here you have the same formulas, you cannot conclude that over there they are the same, and then over here also must be the same. You cannot conclude that sort of things. What is very important here is, if you two functions with same domain two functions u, s, f, comma, g with same domain, say x is said to be, no, it's not correct. I can write like that, but I can write even better. Two functions f and g are equal if domain f is equal to domain of g, and for each x belongs to domain of f, which is equal to domain of g, fx equals gx. Two functions f and g are equal if domain F equals domain G, and for equational domain of. Thus, maybe not much enough ink in this pen. No? Put it this way. Somebody called me, and they have been through this
YouTube channel.
YouTube
channel.
YouTube, and they said, "Sir, did you have hard time with your pens on the very first day?" Thus, two functions f and g are not equal and you see here I am writing two functions f and g are equal if domain of f equals domain of g and for each x belongs to domain of f. My off cannot, nobody can see my off. Domain of f, domain of g, fx equals gx. Now I am saying that two functions f and g are not equal if what? This span is too big point. If I write by this one, difficult to erase the board, no? If I write by this one, not difficult. But, Kutava, two functions f and g are equal if domain of f equals domain of g and for each x belongs to domain of f, each is equal to domain of g, fx equals gx. So if they are not equal, two functions f and g are not equal if
domain of f is not equal to domain of g.
Domain of f is not equal to domain of g. O
for each x belongs to domain of f not equals to domain of g.
But here, I have it here, for each x belongs to domain of f equals to domain of g, fx equals gx. There is a comma here. For each x belongs to, because they are equal, I mean, if you want, I can put this one in parentheses because they are the same. No? For each x belongs to domain of f, fx, comma, can you see the comma?
Yes.
Fx equals g. So you said thus two functions f and g are not equal if domain of f not equal to domain of g O
each x belongs to domain of f equals to domain of g, fx not equals to gx.
Kuta, is he correct?
Not sure.
Not sure. Is he correct, Patty?
Can I repeat the answer? Can I
No, I will repeat what he said. He says the two functions f and g are not equal if domain of f is not equal to domain of g O. I will put the comma. Oh no, I don't need because it is one thing. O for each x belongs to domain of f within parentheses equals to domain of g, fx not equal to g of x.
He said for each, right?
Yes.
It should be for some x belongs to domain of f equals domain of g, fx not equal to g.
For some, what is this pen? Who provide pens to this class?
Probably the uncle.
Maybe I should bring a vade to him next day. Ask him to give me that for some x belongs to domain of f. Which is equal to it. We don't have to write that part, but anyway, it will be right. For some x belongs to domain of f, fx not equal to g of x. If you can tell me this, then you are a good student in the sense that you have understood what I have been preaching since the first day. But the thing with the book is that from the book you are not getting that impression. This is how I write when I teach. Because in his case sometimes he says two functions are equal provided they have the same domain, and for each x in not in the same domain also he says, let's say he said sometimes he says same domain, and for each output they have the same output. When you write precisely, it is easy for you to see the negation. F and G are equal. Good thing is you said, you began correct, domain of F not equal to domain of G. Oh, then you forget about negation of for each. Oh, you could have said there exists instead of for some, there exists x belongs to domain of F. Then you have to have such that. Fx not equal to Gx. From the book you don't get that logicalness. That's the thing I am saying, I'm not happy. Because quite often I will point out to you next day now, I guess we are about to finish 5 more minutes. You have to see that everything is logical. Don't sort of try to say anything in your own. Two functions are equal if they have the same domain, domain of f equals domain g, and for each x belongs to domain of f, fx equals dx. Thus two functions f and g are not equal if, as you said, domain of not equals to domain of g. Oh, for some x belongs to domain of f, fx not equal to gx. Oh, you can say other way. There exists, I have to take some English class. There exists x. There exists x belongs to domain of f, or whatever domain of g, such that fx not equal to gx. You have to see that logicalness. That is very important. That the book is sort of not giving a place to that. Quite often he does it. So something. That's what happened here. These two functions, they have the same domain. However, I got -1. Then you say I am justifying this statement. I took -1. -1 belongs to domain of set. I am showing f of -1 is not equal to g of -1. Therefore, f is not equal to g. Actually, I verified this statement. I verified this statement. You are good to say that domain of f not equal to domain of g. Oh, you said it correct, but to the contrary, you forgot here this thing. I don't blame you because that's why I told you gradually I will make it logical so that you will see it right away. When you say A is subset of B, every element of A is an element of B, then logicalness goes away. You have to say A is subset of B if for each x belongs to A implies x belongs to B. Then if you want to say A is not a subset of B, there is some x such that x belongs to A and x doesn't belong into B. Do you see what I'm saying? If you learn like that, you become very sharp and nobody can attack you. Nobody means not very straight. I mean, logicalness cannot be attacked if you begin to write like that. So that is why you understood my statement now. Let me write it again to make sure that you get it. we say A is subset of B. If for each x belongs to A implies, I don't like this symbol, but doesn't matter anyway, implies x belongs to B. Now, put that, well, A is not the subset of B, hence A is not the subset of B if, put that,
For some x.
shall I write there this x?
What?
Instead of for some x, shall I write there this x? Same thing, no?
Yes.
There is
Exist x.
there is x. If I write there is x, there are two words I must write. What are these two words? As soon as you write there like this, there are two English words. Putava? Such that. There is such that. It's very important. And you keep up the direct this exercise. Both three of you are good, but book is not logically going somehow. I don't like it. Anyway, but you now coming back to you, direct this is my yes, nobody can see my yes. When I was the head of the department, community, I sometimes write things to my secretary. I write pa 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 pa. I cannot read mine. Then I go and ask the secretary, her name is Swarna. Swarna, can you read it for me? Then she said, "Sir, you wrote it, no?" But it is like that. I cannot read my X. So direct is X such that, Puta, you are correct when you say for some. I didn't say you are incorrect. Such that
X is not an x is element of A. Does not imply x element of B.
oh, Puta, you are not doing homework. So this is not good. I am the one who taught you a simple thing. Negation of for each is, you said for some, but I wanted to write this such that part to make sure that you get it. For some is correct. There it is X such that make a novena in single. Such that it is not the case this one. So what is it then? Putava?
X belongs to A, and X doesn't belong to B.
Very good. If I had money, I would have bought you a visa. Very good, Buddha. X belongs to A and X doesn't belong to B. When you write the definition, negation, you have to have it logically. This is not, you are not writing in your own, it comes from here. X belongs, negation of X implies Y, not X implies Y is X and not Y. Very important. දැන් නම් කොහොම කියොත් මට නම් ඉගෙන ගන්න වෙනවා. මම ටිකක් සර් මෑන් කෙනෙක්. කිසියද පුතාලි.
YouTube पे गया
So I have to be down. Anyway, right?
yeah.
This is why I told you, quite often negation, he writes as if it is something new. This is not new to this statement. when you say A is subset of B, meaning A is not the subset of meaning is attached, follows. So he writes quite often A is subset of B, then he new statement. So it's not new. We didn't write this. I mean, of course I wrote, but the contrary statement comes from the negation of this line. Now this is own, I should go. Anyway, so you understand? So I will have to do quite a lot of changes when we are using the book. So let's quit for the day, no? Then, you should do that in the